Hello guys and welcome again to another video of Math 030. So for this video I will discuss a lot of things about partial derivatives in general, and let's get into it. no? So for the intended learning outcomes, you can just read this on your presentation slides that I will upload for later. And then the outline is the most important one, or the more important one. Well, to save a little bit of time. So we have the functions of several variables, limits and continuity, and partial derivatives. So what is a function of several variables? No. So moving on from vector functions and referencing the previous lessons that we already know, well, regarding algebra, is that if you can recall, no, we have a function. If we have a function of x, no, which is also equal to y, we have x as our independent variable. Sorry, independent variable, and then we have this y itself, which is your dependent variable, or representing this y. Okay, so now if we have more than one independent variable, we can call this the function of several variables. So if we have, let's say, the function of x and y, okay, we represent this usually as the height axis, the the z axis, wherein we have two independent variables, okay, and then we have one dependent variable, which is also this f of x, y, or z. So instead of just having one independent variable, one predictor, we have two predictors for our dependent variable. So basically, these two independent variables will map a single value, which is our z axis value coordinate, no, or the dependent variable. Now, that's basically it, no. So we can find the domain of your, no, we can see this as the domain of your x and y, which will map to a z function, which should be unique, ano. So we will discuss about the uniqueness of the domain and range. Now, for an illustrative example, so instead of having one value for x, one value for y, no, and then it will have a relationship between the two. We have again, we have function of x, it will map to y. So we have x, and then we will get y. Now we have a function of two variables. For an example here, we have L and K. So these are our independent variables. Okay. And then this will be your function to represent the relationship of this two independent variables to our output function, which is also your dependent variable. So this as a whole, your p-value is actually, or you can just write this, no? This is your dependent variable. So what does this mean, ano? Or what does this example mean to us, no? So this is actually called the Cobb Douglas function. Okay, so what does this mean? It basically maps the relationship between labor, capital, and the production, ano. So this is just an abstract representation of Cobb Douglas function, but let's say you have 100 units of labor, you have 200 units of capital, so you have 100 units of labor, 200 units of capital. You can map that out into our surface, ano? So you will have here a height that represents this, let's say somewhere here, I don't know, no? It is not usually, it is harder to visualize. Your height here is this, and then this will be your, let's say this is about 80. So for a labor of 100 and a capital of 200, you will have a production of, let's say, 80. Okay? So instead of just a line, no, we have two axes in this one. So we have just x and y axis. For functions of several variables, especially if you have two independent variables, this will be a three-dimensional space. So you have x, you have y, and you have the height z. So basically, this x and y will predict what will be the height of your or what will be the height z. Okay, so let's get into it, no, and let's start remembering the previous concepts in algebra and calculus. we can find the domain, we can find the range, we can evaluate the functions. So let's say we want to evaluate the first function here. Okay, so this will be for f, sorry. So if f of 3, 2, that is equal to what? So you can just substitute the value here. You have 3, you have 2, and then 1, and then over 3 minus 1. So 3 minus 1. So this will be just square root of 6 over 2. So this will be your evaluated value. So this will be your height, no? And then for this one, we have again the function of we want to evaluate at f of 3 of 2. So this will be 3. So x is equal to 3. And then we have ln of, we have 2 squared and then minus 3. And then evaluate this, we have 3 ln of, so this will be 4 minus 1. So this is ln 1. So ln 1 is just 0, basically. So we have 0 times 3, which is 0. Okay. So this will be the evaluation of the function at this given given condition. So we have x is equal to 3, y is equal to 2. That's it. And then if you want to find the domain and range of the function, actually you just want to find the domain here. So if you want to find the domain, what are the possibilities here that it won't be continuous, So for square roots, the problem here is that it cannot be negative, right? And then for the new denominator here, for the first function, this cannot be 0. So we have two conditions for this domain. So x plus y plus 1 should be greater than or equal to 0, meaning it should be positive. And then for the other one, so this is for the first function, okay? And then for the second condition, we want the denominator to be not equal to 0. So x minus 1 is not equal to 0. So if you simplify this, actually you don't need to simplify this anymore, but we can write this in a different way if you want. But I think this is fine anyways. But you can write this as well in this form. This is also another form. And then this one can be this in this form. So you have these two conditions that represents the domain of your function. So therefore, the domain of your function is this should be written in this way. So your function f of xy is an element wherein x plus y plus 1, or this one, no, you can write this one as well, is greater than or equal to 0. Okay, and x should be sorry, this should be 1, no, sorry, x should not be equal to 1. Okay, so that's basically your domain. So if you visualize this, guys, if you visualize this, I hope you're already familiar with inequalities. Although, how do we draw an inequality? So if you have an inequality, guys, if this is your form, then you just have to draw this function. If you want to draw this function, so I will save you the time, but this is how we draw this x plus y plus 1. Okay, so this is your x plus y plus 1. So this is the origin. You have x plus y plus 1 is equal to 0. Now, if you have greater than 0 here, then it should be this, no? This area around here. And then the problem here is we have another condition. So knowing that this will be your domain, so anywhere between or anywhere in this plane of this x and y axis, this above of this plane will be a valid solution or a valid domain for our function. And then we have another extra condition. So when x is equal to 1, it will not be possible. So we have to also include or actually exclude x is equal to 1. So basically this is your drawing. Now if we have a solid line, if it's a solid line, guys, we include this line, no? Because this is also greater than or equal to. But if we have not equal to, so this actually we have this singular line here. which is not included in this area, should be in what do you call this, dashed lines. Okay, for the second function now, so we drawn the first function. What is the condition here? Will where will this will not be or we will have a problem here. So for logarithmic functions, they should not be equal to, or they should not be equal to 0 or a negative number. So y squared minus x should be greater than 0. Okay? So if we simplify this, this will be y squared is equal, sorry, not equal to, but greater than x. Okay? So how do we now do this? So what does this look like? No? So if we make this an equal sign, this will look like a parabola. And to be specific, this is our a parabola, a horizontal parabola opening to the right. So this will be a parabola here, another parabola here. This will be your x is equal to y squared. Okay. And then the problem here is there is no equal sign. This is only greater than. And then how do we imagine this if this is greater than? So if this is greater than, or y squared should be greater than x, we should remember, or actually the best way to do this actually is to try values of x and y. So if your x is equal to, let's say, how do I do this? What do you call this? Not try. How to explain that? So your y here should be greater than x, no? So basically, if this is your y squared, this point is y squared, then greater than y squared should be upwards, ano? So this area around here should be greater than y squared. Now, if we have this format, actually it should not be a solid line. So I should create a dashed line for this one. So y squared is equal to x is not included in the domain. So basically, outside of this, y squared is equal to x. We have this area around here, this blue portion. Okay, so to write this down, we have f of xy as an element. Sorry, not close. As an element of x is you can write this in this form as well, and then that's it. Okay, so this will be your domain. Now let's move on and not just find the domain but also find the range. So again, we have this given. If you have a square root, the square root, the value or the expression inside the square root should be always a positive, or not, it shouldn't be a negative number. So 9 minus x squared minus y squared should be greater than or equal to 0, no? And if we simplify this, we have we can transpose this to the other side. We have x squared plus y squared is equal to 9, or we can say x squared plus y squared is less than or equal to 9. Okay, so this will be your domain, or you can write this as well in the other way around. There are different ways to show this. So your domain here is the function of g of xy, or we could call this z, has this condition. We have x squared plus y squared less than or equal to 9. Okay, so this will be your domain. How do we now find the range? Okay, so if we look at this, what should be the range of this? No? So if we know that the domain should be less than or equal to 9. So basically the sum of this, no? We can write this as, well, the sum of x squared and y squared. Okay, we can write this in this form. We can factor out the negative sign. So this x squared plus y squared should be less than or equal to 9. So what does that mean? So it could be from actually from negative, no, also. I think you can also do negative. But we know that this will never be negative, right? This will never be negative pala, no? So x squared plus y squared we have to add another condition here. This should be greater than 0. Anyways, it is understood here. So as we can see, no, the maximum value of here, this one is, we have the maximum value of 9, right? The maximum value of 9 here, and the smallest value here is 0. So this is the maximum value, and then the minimum value is 0. Okay? So we have 9 minus 9 and then 9 minus 0. So if you find the square root of this, we have 0 here. This will be 3. So therefore, the range here, if this is included, since this is less than or equal to, then the domain here, sorry, the range here, okay, which is, oh, domain pala to, no? Wait a minute. This should not be a function pala, no? I forgot. XY lang pala to, no? So the domain here should not have the value g. So the range here will be g of xy, which should be from 0 to 3. So including 0 and 3 for this g, or we could call this z, or we could call this g of xy. Okay, so that will be the domain and range. And if we find, no, if we want to sketch this one, so if you want to sketch the domain here will be just a circle, no? So a circle with h and k at 0, 0, as you can see, and then your radius will be 3, no? So this will be a circle with radius 3. So this will be your x squared plus y squared is equal to 9. Now, if we say that this is less than, therefore this will be within this curve. Okay? So also including this, no? Since this is less than or equal to. Okay, this is your domain. Okay? Okay, so let's move on and let's now figure out how do we sketch the graph of a function or a function of several variables. Now for this one, this looks, I hope this looks familiar. This is just a plane, no? And we know how to visualize a plane. no? But how do we do this in a much simpler way? There are different ways, and the easiest one is to find their intercepts. Ano? So as you can see here, we have three axes or three axes. Then therefore we have three intercepts that we can define. Okay? Sorry, not this. This is the z. So this is positive z, positive x, positive y. So if we have this function, basically this also means z is equal to 6 minus 3x minus 2y. So what will be the intercept in x? What will be the intercept in z? What will be the intercept in y? So when x, we're talking about the intercept in x, no? So everything is 0. Remember that, no? And then for z, sorry, and then the x coordinate will have a value. Now for z now, everything will be 0 except the entry for z. And then for y, everything will be 0 except for the entry in the y. So to figure out this value, we can substitute zeros here to find the intercepts in x, y, and z. So let's say we have, if let's start with the x intercept. We have, if y and z is equal to 0, which is this one, then we can substitute here y and z is equal to 0. So we have, uh, why does it, okay. So 0 is equal to 6 minus 3x minus 2 times 0. So we have x is equal to, so this will be simplified into 0. So 3x is equal to 6, therefore x is equal to 2. So therefore we have 2 here. And then we have if for the z intercept, we have if x is equal to 0 and y is equal to 0, or just write this as, hold on, why doesn't it work? Yeah. So we have here uh z is equal to 6 minus 3 times 0 and then minus 2 times 0. So this will cancel out. So z is equal to 6. So therefore this will be 6. And then if x is equal to 0, or actually x and z is equal to 0, we have 0 is equal to 6 minus 3 times 0 minus 2y. So this will be 0. And then we have 2y on the left hand side is equal to 6. So y is equal to 3. So we have here 3. Therefore, what does this mean? So we have a surface, or this surface that has this coordinate, which has this intercepts. Now, if we know that this is a plane, since this is a linear function, then therefore we can connect this, no? Basically, we can just connect this 3 points, and then we can extend this in this all directions, and you will have this plane that is extending in this three directions. Okay, so that is how you draw a function. You usually find the intercepts, and then that's it. You can just connect the dots, and then you can expand the surface. Although this is not applicable for nonlinear functions, which we will in which at which we will discuss also later. Okay, so this is a more a method more scaled version of what we did. So this actually extends, no? This is not limited to this triangle. This is extended infinitely through all directions. Okay, so now let's graph another function. We have a nonlinear function, which is also our example before. Okay, so again, we can map this out as instead of g of xy, we can say that this is z, and then equals to the square root of 9 minus x squared minus y squared. So now if we say this is a function, if you can remember in your calculus class, we only take the positive square root. So remember that we only take the positive square root for functions. So take note of that the z value here, take note that the z value here should be always, so z should be positive or greater than or equal to 0. So if we simplify this, we can simplify this. This will become z squared. So square both sides is equal to 9 minus x squared minus y squared. And then rewrite this, no? We can transpose this to the other side. So we have x squared plus y squared plus z squared is equal to 9. And as we have here, what do we have here? This is actually an equation of a sphere. Okay? And what is your center? So the center here is equal to 0, 0, 0, right? So whatever is in here, so minus 0, minus 0, minus 0. But since we don't have a 0 here, we don't have a value, no, this is not x minus 2 squared, this is only x squared, then therefore your h coordinate is 0, and then k is equal to 0, l is equal to 0. Now for the radius here is the square root of 9, which is 3. So if you visualize this in three-dimensional space, this will be a sphere. But emphasizing this, guys, the z should be greater than or equal to 0. Since this is a function, this is an equation, no? Functions and equation are different, no? When we say a function, we only map our dependent variable as a single value, a unique value that maps out from two independent variables. So if you visualize this, we have this, no? So again, why is this just half a sphere? Because we know that the z, no, should be greater than or equal to 0, meaning it should be positive. So if it is below, then it will be negative. So this is z negative, this is z positive. Okay, so remember that. Okay, so we have more functions that we can graph, but this will be difficult to do manually Analytically, we usually use a software to visualize this. But although if you try some values here, you can have a better idea of, let's say, what is if x is equal to ganyan, y is equal to ganyan, what will happen to this function. So you can actually identify, even if you cannot draw this by yourself, you can identify which function is this, which function is this, assuming that you have also the mathematical equation that represents at least the choice between these two. So for this function, actually this is a Gaussian function, or the error function, the normal distribution function, and it will look like a normal distribution, as you can see here. And then for this one, if you have this function, there will be an oscillatory behavior. So as you can see, there are some oscillations, no? The sine function is oscillating. Okay, anyways, you can explore this yourselves on how to draw, or how to use software to draw the graphs of given functions. Now, since we are talking about graphs and functions, or graphs of functions of several variables, let's get into the contour maps, no? So as you can see, it is quite hard, no? From this point pa lang, it is quite hard to visualize or draw the function of several variables. Now, we could simplify things using level curves and contour maps, no? So imagine this is your graph, no? Using a software, you have this drawing, no? But actually, you can do this yourself. Instead of individually, no, you can do a trial and error. What is this point? What is this point? This point and this point. And then using interpolation to get this surface. Actually, there is a lot of things that is going on with graphing surfaces. What you can do is you can assume a value of z. Okay, you can assume a value of z, and you can observe what will happen to your function. Ano? So if you equate this as equal to, let's say, 0, you can get a behavior of this. Y is probably equal to 0. No? So we can represent this as a function of this. No? So we can divide this by sections, or planes, actually planes. You can have this plane, and then this will have an intersection here. You can have a plane here, and then it will have an intersection that looks like, this will look like this, somewhat like this. And then you can have an intersection here, you can have a plane here, and so on. And then you will have an intersection that looks like this. So basically, you can assume a value of z. So there are different value of z's here. Let's say this is equal to, I don't know, 2, and then you have 1, and then you have 1/2, no? I don't know, but you can represent this. You can just basically cut your function into half, no? Or sorry, cut your surface into a plane. So basically what we did here, this circle here is actually called a level curve, ano? So what does that mean? Because your z here is your level, okay, you can assume a value, a level, and then it will map a curve based on that level, which is also this, no? This is your level curve. Now, if we do more of the level curves, if we assume a lot of values of z, then what we can do is we are developing a contour map. So if you draw a lot of level curves, you can have what we have, a contour map, no? Okay? So what is the difference between the two? A level curve is just a singular curve. A contour map is the collection of level curves. Okay, so if you do this, no, as you can see, no, if you cut this into slices, you will have this curve. Now the problem with contour maps is it doesn't usually visualize the height, no, but you can get that information if you write a value here. So let's say this is z is equal to 2, z is equal to blank, z is equal to, and so on, and then z is equal to n, so that we get a better idea of how we draw this in three-dimensional space. Okay, so one example of this, no, a much fitting example of visualizing a contour map is the temperature distribution or the average temperature distribution of the world or Earth. So in here, we have the average temperature within the equator. So we are here. So the average temperature should be around 26 degrees. And then around this portion, you have 32 degrees, 37. And then you have here a lower temperature above the hemisphere or the near the north pole we have 10 degrees, 15 degrees Celsius, and so on. So basically what we did here, we have the level curves, the temperature within that line, and then if you have the collection of this level curves, we have the contour map. So you can visualize this in three-dimensional space wherein we have a peak here, no? So this will have a peak here, and then we have a lows, no? A low values in this. Okay. So you will have a mountain here that looks like I won't draw this anymore, but there is a peak here, and then there is a lower value here. Okay, all right. So moving on and discussing now a new subtopic, which are limits and continuity. Let's compare the behavior of two functions. Now, some functions can be complicated than others, no? And let's say we have these two given functions. So, observing this function, there are discontinuities within this function. What are discontinuities? So, discontinuities are just points in the or just points wherein there could be an undefined or indeterminate. So, let's say for this first example, when x and y is equal to 0, no? So if x and y is equal to 0, as you can see, no, this will become, the function will be 0 over 0. Ano? Same goes around here. If we have x and y is equal to 0, this will also be 0 over 0. So we have an indeterminate in your differential calculus. Therefore, we have to analyze this functions at these points if they are continuous or discontinuous. So we want to find the limit. So in finding the limit, it can be it is actually tricky, no, to find the limit of a function if you have this. So let's get into it, no, and then let's say we want to try and what do you call this, we can try and brute forcing, no, or we can try different or trial and errors for values of x and y that is near this value of 0. So basically, we can try values of x is equal to 0.001, y is equal to 0.001 to try and understand what is the behavior function as it approaches to the value of 0 for both x and y variables. So what we're doing here now, what am I discussing here is actually a numerical method of trying to find the limit of a function. I hope you are already familiar with this. So if you tabulate this trial and error, that basically what I'm trying to say is that if we substitute the value of, let's say, x is equal to -1, y is equal to -1, we can map the value of the function, which is 0.455 for the first function. And then for 0, we do not have an no defined solution, and so on. So as you can see, if we want the function of xy, no, as the limit, okay, or actually that's not how I should write this. So you have this f of xy, uh, which is the function here. If this function approaches this as this limit approaches 0, okay, okay, as you can see, this will approach to 1. So why did I say 1 here? Because as you can see, the behavior of the function, it gets closer to 0. As it gets closer to 0, it approaches to 1 in all directions, not just in this vertical and horizontal directions, but also diagonally. Ano, it should what do you call this? It should approach to the value or the limit in any directions, in all directions. No? But for the g of xy, okay, for the g of xy, as you can see, okay, so the limit as this function approaches to 0, well, this will approach to 1, this will approach to -1, this will approach to 0, this will approach to 0. So they do not agree. So if your limits or your function as it approaches to some value 0, 0, and it doesn't agree in all directions, so at least one direction that is doesn't agree with, then the limit does not exist. Okay, so remember that. Okay, or we can call this DNE, for does not exist. Okay, so let's have an example, or sorry, not yet pala, no? So a formal definition of the functions of two variables, we have uh, the function of x and y, and then if you want to find the limit of our function f of xy as x and y approaches this pair, no, a and b, we have the value L as your limit. Now, the condition here is that for different direction of this, no, at different direction, approaching at different directions, approaching at different directions, it should always arrive at this L. So if there is a difference in values at different directions as it approaches, coming from the left, from the right, upward, downward, diagonally, then it will not have a limit. Okay? So show that the given limit does not exist. So we have this function. And we just want to prove that this limit does not exist. So how do we do that now? Okay? How do we do that now? So basically what you can do, what you can try doing is, you can let first x is equal to 0. So what we can do here is, we can substitute 0 here. So since x and y is equal to 0, we can first substitute x is equal to 0. So if x is equal to 0, what happens is that the limit will simplify into y approaches 0 of we have 0 minus y squared, so negative y squared all over y squared. So as you can see, this will approach to, so we can cancel this into -1, okay? And then we can try again. If y is equal to 0, then the limit will simplify into x approaches to 0. And then if this is 0, we have only x squared over x squared over x squared, which will be cancelled out into +1. And now, as you can see, if they do not agree, does not agree, then at this point, we can just already say that does not exist. The limit does not exist. It's that simple. Okay? So as it approaches to 0 from x is equal to 0, now as you can see the direction here, this will not be equal, so this will be -1 and this will be +1. If they do not agree, the limit does not exist. So another one, we have another function here. If if the function is xy over x squared plus y squared, does the limit f of xy as x and y approaches to 0, 0 exists. So we can do that again, no? So if x, no, so we can just substitute x here. X is equal to 0. Okay, we have what do you call this? We substitute 0. This will become so this will be 0, right? So this will be 0 over y squared, right? So the limit as y approaches 0 of this. So as you can see, this will be 0, right? Okay, we're good with that. And then if y is equal to 0, so the limit simplifies to, so this will now be 0, So 0 yung numerator, and then this will be 0. So this will be x squared, and then the limit will be as x approaches 0. So this will also be 0. Okay, so are we good? So the limit exists and this is equal to 0. So actually not that fast, no? So we know that the relationship between x and y, we know that x and y is equal to 0. So we can know that basically there's a case where x is equal to y. So basically we can substitute x is equal to y here. So if we substitute x is equal to y, let's say this will be equal to y, equal to x. Since x is equal to y, this will be x squared, right? This will be x squared over x squared plus x squared, diba? So the limit will now be as x approaches 0 of this, right? So this will become, if you simplify this will become x squared over 2x squared. We can simplify this, right? So the limit will reduce into 1 half. Ano? So as you can see, this does not agree, no? So this does not agree. Well, this 2 agrees, but this does not agree with 1 half. So we can say that the limit does not exist again. So as you can see, it is easier to prove that a limit of a function of several variables does not exist than to prove that it exists. Okay? So just one disagreement will lead to a does not exist limit. Okay? So the visualization of this is we have this function. The limit will approach 0 from the y, and then the limit will approach 0 from the x. But if we say that y is equal to x, then the limit will approach to 1 half. So the visualization of this graph is that when x is equal to 0, there is a discontinuity, you know? So we call this the discontinuity. Okay. Okay, so we have the properties of limits. So we can add limits, we can find the difference between limits, we can multiply a limit by a constant, and then we can find the limit of products, we can find the limit of quotients. So basically, the limit operator just distributes in sum and difference and also in products and quotients. Okay, so let's say we have this, we want to find the limit of this. So what does this basically mean if we want to obey the limit rules is that this will now become the limit as xy approaches to 1 half, and then we have x squared y cubed, and then minus the limit as xy approaches to 1 and 2, and then we have x cubed y squared, and then plus we have 3 times the limit of xy x, and then plus 2, sorry, wala pala limit, no? Sorry, xy approaches to 1 half. Yeah. And then we have limit y, and then xy approaches to 1 and 2. Okay, so basically just an expansion, no? And then we can evaluate the limit individually. So this will be equal to we have 1 squared times 2 cubed, so this will be 8, and then minus we have 1 cubed, so 1, and then 2 squared we have 4, and then 3 times the limit as x approaches 1 and y approaches 2. So we just substitute here 1, so 3 times 1, so plus 3, and then we have here xy, so substitute the y here is equal to 2, so 2 times 2 is equal to 4. Simplify this, so this will be 8 plus 3, which is equal to 11. Okay, that's it. It's that simple, no? So now let's discuss about the continuity. So if the limit exists in this point, no, as we go on with the different directions, then it is continuous. So basically, if limit exists, it is continuous. If limit does not exist, then it is discontinuous. Okay, that is the simplest way to describe this. So if you have this function, ano, if you have this function, you can define the discontinuity here, no? As you can see, where will we have a problem here? Okay, so the denominator, right? So this should not be equal to 0, right? So we have to say here that x squared plus y squared should not be equal to 0. Ano? So it could be continuous everywhere else, but it might not be continuous at this point. Okay? So this should not be equal to 0. Okay? And if this is not equal to 0, then what are the categories that will be equal to 0? So we can find the limit as x and y approaches 0, okay, of x squared minus y squared, and then over x squared plus y squared. Okay, so what can we do here? No, so if x is equal to 0, then this will reduce into the limit as y approaches 0 of we have negative y squared over y squared, right? So this will be negative 1, right? And then for if y is equal to 0, which is this, we have the limit as x approaches 0 of, so we will cancel this y squared and y squared. This will be just x squared over x squared. So this is the same example as before, so this will be equal to 1. So if this there is a disagreement where we have different values for different approaching values, then the limit does not exist. Okay, so we can say that this will be discontinuous, no? Uh, this will be discontinuous at this point. Well, although we can set a value for this. Let's say this is the function. We can set this at this discontinuity. We can set if xy is equal to 0 0. We can let the value of this f of xy is equal to blank, no, if you want, no, like say you want this to be 0, you want this to be 10, and so on. So it depends on the person, no. If the limit does not exist, you can define using piecewise functions. So it will look something like this. If this is discontinuous, you have a piecewise function wherein you could say x squared minus y squared, x squared plus y squared. This is defined if xy is equal to or not equal to 0 0. But if xy is equal to 0 0, then you can define a value here. Let's say you could say this is 0, and say this is 1, and so on. Okay, so it depends on you what you want to put here for discontinuous functions. Okay, now for the last one, sorry for taking too much time. We have the partial derivatives. So the partial derivatives is just, excuse me there, it's just another concept that we are already familiar with in differential equations, but we will have even more examples. So if we, let's say we want to find the partial derivative of the function with respect to, no, so if say we have f sub x, we have the subscript, and basically that means with respect to x with respect to y. So find the partial derivative with respect to x of this function, find the partial derivative of this function with respect to y, and so on. So this is the definition limit, the limit definition of a derivative of a function of several variables. I won't discuss this anymore to save a little bit of time, but there are different ways to notating partial derivatives. So you can notate the partial derivative of this function in this form. It could be in this form. It could be in this form. There are different ways to show this. Yeah, so I have this laser pointer. So you can represent this in this point and so on. So as you can see, there are different ways. So usually we will use this to make things more compact, but sometimes we have to use this, or some textbooks might use this or this one. No, actually this one is a little bit tricky, no, but this is kind of useful as well. So what does this mean? So this means that one is your first independent variable, and 2 here is your second independent variable. And usually we notate this as the first one is x, the second one is y, and so on. Okay, so again, no, if you want to find the partial derivative of the function with respect to x, we regard every other variable, no, every other variable as constant. So if you have more than one independent variable, well, let's say you have z as our another independent variable, then we let y and z as our independent variable or as a constant. So again, no, this will be the variable of integration, sorry, the variable of differentiation x, and everything else will be a constant. Okay, and then same goes for y. So it will be, actually it should be x, no? I have another correction here. I'll just change this later on. Okay, so that's it. And then, for example, here, if we have this function, find the partial derivative with respect to x and with respect to y. So if you want to find the partial derivative with respect to x, we are just finding the derivative with respect to x. So the derivative of x cubed is 3x squared, and then we regard this as a constant. So we just differentiate this and this. So this will be plus 2x y cubed. Okay. And then evaluating this at this point, we can just substitute the values. So if we want to find f of 2 and 1, this will be equal to 3 times 2 squared plus 2 times 2 squared times 1 cubed. So this will be, we have 3 times 4, we have 12, plus 2 times 2 squared, we have 8. So this will be equal to, huh? 3 times, um, right? This should be 20, right? We have 2 negative 2y squared. Hindi, but anyways, this should be 0, right? Okay. Huh? Why is my notes not the same there? Oh, it should be 2 times 2 pala, no? Okay, sorry. This should be 16. So this is 2 times 12 plus 4, which is equal to 16. Yeah. Okay, so to find f of f sub y, which is the partial derivative with respect to y, so we will now find the derivative of y cubed and y squared. Now this will be 0, since the derivative of a constant is 0. So we can start here. So we have x squared, and then the derivative of y cubed is 3y squared. So I will just put the constant here. So 3y squared, and then minus, we have 4y. So if you want to find the function or evaluate the function at 2 and 1, we can just substitute values of x and y. So 3, 2 squared, and then 1 squared minus 4 times 1. Okay, so this is 12 minus 4, which should be 8. Okay, so that's it. How do you find the partial derivative? It's that easy. Okay, next one. So f of xy is equal to sine x over 1 plus y. Calculate the partial derivative of f with respect to x, partial derivative of f with respect to y. Now, this might be a little bit tricky, but let's go on and solve this one. So if you want to find the partial derivative with respect to x of this function, or we can just rewrite this as f sub x, this is equal to, so we want to find the derivative of the general function, no? So that is the rule of differentiation. So the derivative of sine is cosine. And then we will just retain this, no, for now. And then we will do the chain rule. So the chain rule is basically find the derivative of, so I'll just write this for now. Find the derivative of x over 1 plus y. So we know that y is a constant. So therefore, the derivative of this is basically, if you visualize this, we can just factor out this to as 1 over 1 plus y, right? So we want to find just the derivative of x. So the derivative of x is just 1. So therefore, this should be multiplied by 1 over 1 plus y. So if you simplify this, this will be, let's put this as It can get confusing if we multiply this by each other, no? So this will be equal to 1 plus, 1 over 1 plus y, and then cosine x over 1 plus y. So this is your partial derivative with respect to x. Now to find the partial derivative with respect to y, or f sub y, we will find again the derivative, no? So the derivative of sine is cosine, okay? Derivative of sine is cosine, and then we have x over 1 plus y again. And then this one, we want to find the derivative. Actually, this should be partial derivative, no? Not t. We have the partial derivative with respect to y of x over 1 plus y. So we treat x as a constant. So we're trying to basically find the derivative of some constant. So parang a over 1 plus y. So how do we find the derivative of this? We have to use, dito kailangan na natin ng quotient rule. Quotient rule. Okay? Or pwede na naman, no, to simplify this, pwede pa rin naman siyang gawing product rule para mas simple lang. So to make things simple, you can rewrite this as, this is equal to x times 1 plus y raised to negative 1. I hope this makes sense already. Diba? So if you find the derivative of this, again, okay, we have, so via power rule, we can just multiply this by negative 1. So this will become negative x and then 1 plus y and then raised to negative 1. So, sorry, negative 2 kasi minus 1 pa. Okay? And then simplifying this to make things much more standardized, no, kung paano natin sulat. So we have negative of x over 1 plus y squared and then we have cosine x plus 1 plus y. So this will be your final answer for the partial derivative with respect to y. Okay? Now, to visualize the interpretation of partial derivatives, again, pag sinabi natin partial derivative, we assume that the values or the other variable are assumed constant, no? So, if let's say you want to find the partial derivative with respect to, let's say, y, ano, with respect to y, so we are assuming that the values of x is constant. So let's say this is the value of x that is remain constant. Then you will have a curve that looks like just a two-dimensional curve. So if you find the tangent line of that two-dimensional curve, then you will have the slope of this tangent line. So basically, the tangent line, when x is equal to a constant value, you will have this slope of this tangent line. So again, to visualize this line here is the slope of the tangent line, which is also the derivative f of y, okay, assuming a value of a and b. Okay, that goes the same with this one. So this line, we assume that y is constant, so this is the constant value of y. So everything here in this plane will be a constant value of y. So the slope here of this tangent line is the partial derivative in x of AB. Okay. Now, let's find again the partial derivatives, no? Sorry, of this function, and then let's see how does this represent, how is this represented in the graph of this function. Okay, so we have this, so we want to find fx, no, or the partial derivative of f with respect to x, which is, actually we can evaluate this already later. Sige. So this is a constant, so cancel out. We have negative 2x, okay? And then therefore, f of x of 1, 1. So substitute 1 here. So we have negative 2 times 1, so negative 2. Okay? And then for fy, we have, this will be 0. So assume everything is constant. Derivative of this, so we have negative 4y. So substitute the value, which is 1, 1. So substitute the 1 here, we have negative 4. Okay, that's it. That is our answer for the the values. Now, to visualize what does this mean in our graphs, on our graphs, is that we have this, no? So if we retain for number one, for the partial derivative in x, so this is your partial derivative in x of 1, 1. It is the slope of this tangent line. So what does this mean? If you want to find the partial derivative with respect to x, so x varies, y is constant. So what I'm telling here, guys, is that if this is your y-axis, then the y values here are constant. So it extends throughout here. And then if you draw a line representing this curve, or this intersection here, will be your partial derivative. Ano? Okay, the collection of slopes here will be your partial derivative. And then at this specific point, you can find your slope of your partial derivative. Okay? And then same goes for here. Fy of 1, 1, y varies. Okay, and then x is constant. So x here is a constant value. So it doesn't change. So the cross sectional now, if you look at this point, it will just be a line x is equal to 1. Ano? If you have this your as your x axis, and then this is your z axis. Ano? So this line will be constant where it will be this point. So given the value of x and y, you will have the slope of this tangent line at this point. Okay? So I think this is matatapos na pala tayo, no? So find the partial derivative of z with respect to x if z is defined implicitly as a function of x and y by the equation. Now we can do also the partial derivatives in implicit form. So if it is not shown explicitly, pwede natin siya yung derivative pa rin using implicit differentiation. Now, how do we do that? Ano? So let's say we want to find the derivative of this. So basically, perform the operation here, partial derivative of z with respect to x, right? Or sorry, not that, but partial derivative with respect to x. So this will be 3x squared, and then this will be 0. So this is 0, and then this will also be 0, right? Not exactly. Since z is a dependent variable of x, we want to find the derivative of z. So this will be plus 3z squared, okay? And then multiplied by, so via the chain rule, you want to find the derivative of z with respect to x. So you have to multiply the partial derivative of z with respect to x, okay? So we have to multiply this and then plus. So we have a multiplication of this. We assume that y is a constant, right? So we have x as our variable of differentiation and then z as our function of x and y. So we have a product rule here. No? So we have 6x times y, 6x times z. So we want to do a product rule of this two. So we have 6x and then multiplied by the partial derivative of z with respect to x. And then z times the derivative of 6x, which is just 6. And then the derivative of 4 is 0. So equate na lang natin sa 0 to. Okay, now simplify. So let's group everything that has the z derivative, and then everything else that doesn't have a z derivative transposed to the right. And then factor out the partial derivative with z with respect to x. So factor this out. We have here 3z squared plus 6x. And then this will be negative 6z minus 3x squared. And then divide this by 3z squared plus 6x. No? So the partial derivative of z with respect to x is now negative 6z minus 3x squared all over 3z squared plus 6x. Now we can simplify this actually, right? We can factor out the 3, right? So this will be actually the negative 3, ano? So negative 3, this will become z, sorry, positive 2z, 2z plus 6, sorry, plus x squared, huh?